So far we have looked at amplifiers, ideal op amps in terms of having nullators and narrators. In case of nullators and narrators, the plus and minus sign is not important. But as soon as we start looking at real amplifiers, the plus and minus sign indicate whether you have positive or negative feedback, and then they have very different characteristics. So this is what we'll talk about this time. So this is an amplifier in negative feedback. It means that the output is fed back to the input at the minus terminal. So in a real op amp, what we have is that you have a voltage here. So in this case, the amplification A, that's the gain of the amplifier, it could be, let's say, 1,000,000, would be the V plus. Let's say this is V plus and this is V minus. So it is the output here, V output, is equal to the amplification into V plus minus V minus. And this is called negative feedback. However, if we look at this case in which the amplifier is the same, but I have flipped the input, and the amplification, as far as the amplifier is concerned, nothing has changed internally, which is it amplifies from plus to minus, and so V output is still, let's say, V plus and V minus. So V output, is still equal to amplification into V plus minus V minus. But in this case, the one thing you can see very easily is that if you have a large output, let's say it's stuck at plus 10 volts. If this is 10 volts, then the 10 volts sort of can feed itself. This is a positive sign, this is at ground, so the 10 volt, as a part of it, feeds itself and can keep feeding itself. So this is called a regenerative positive feedback. It generates itself again and again, and this makes it get stuck at that 10 volts that it started with. So in most of the circuits, what we will be using is negative feedback, and negative feedback helps to control gain. So you have an expected, so control is also expected. You can expect what the gain is. And it doesn't really depend on the exact amplifier using, as long as the amplification is large. But in a positive feedback circuit, you very rarely use positive feedback circuits other than as limiters. So limiter means if you have a signal and you pass it through a limiter, the output you will get will basically be limited to the supplies. And the one place it is used is to introduce hysteresis, which is memory, and we'll look at why hysteresis is important in a second. So let's take the example of, let's say you have a solar panel, and the solar panel is charging your batteries. So these are the batteries. Now, in order to protect the batteries from overcharge. And, let's say your battery is charged and your solar panel can continue giving it power, then this voltage will start drifting up more and more, and that will blow up your battery. So in order to protect your battery, you put a couple of external loads. You want this load to turn on when your battery has reached 14 volts, and you want this load to turn on when your battery has reached 15 volts. So then you need basically something that is a comparator. You want to look at the input battery input voltage. Okay, so I somehow generate some version of 14 volts. One simple way of doing that is putting a resistor divider. Maybe you compare to something more reasonable. Let's say you divide it by 2. So this is some resistor, this is some resistor, and this is some reference voltage. So let's say we find some way to make this reference voltage 7 volts, so that when I connect this signal to that resistor, when it crosses 14 volts, my output says, yeah, now connect this switch, turn this switch on. Now what happens if I turn this switch on? I connect a large load, basically a small resistance across the battery, so that the current from here will now go there and not go into your battery. But generally what happens is that if you just crossed 14 volts, then if you had this battery voltage clearly below 14 volts so far, so it was charging slowly, and it's reached 14 volts now, so this is 14 volts. Then as soon as you connect a large, when you connect a load to it, this voltage will dip, because you're connecting a large load and the solar panel has a resistance inside, and so does the battery. So when the voltage dips, this voltage will go down. Now you'll say, oh, now that the voltage is lower, I should turn off the switch. So the switch will turn off. Immediately the battery voltage will go up again, and then you say, okay, now we have to turn on the switch. So you'll continuously keep turning the switch on and off. So this is of course when it's at that point, and when you turn it on, it will dip, and then you will turn it off as it's dipping. But this will actually happen in a very short time, no? Because as soon as it goes below, this is a very large amplifier, it will immediately turn off. So you'll actually get something like that, going up and down, going up and down, going up, going down, going up, going down, going up, going down, going down. So this is a terrible thing to do, right? Both through your load as well as the solar panel and your battery, you're continuously connecting and disconnecting a load. And this voltage will also look actually the same. I had drawn it just to demonstrate what happens. It will keep going up and down and up and down and up and down and up and down. And that will be the current that you're getting there, and the output also will look the same. So in order to avoid this, usually you're looking for a configuration where it turns on when you reach 14 volts, but it turns off at a slightly different voltage lower than 14 volts. So let's say 13.5 volts or 13 volts, let's say even 13 volts. So I want the switch to turn on when it's 14 volts, but I don't want it to turn off immediately after it goes below 14 volts. I want it to turn off only when it reaches a much lower value. So I'm basically changing my trigger point based off whether the output is 1 or 0. So when the output was 0, to turn on, I wanted the trigger to be 14 volts, but when the output is 10 volts or 1, then to turn it off, I want the trigger to be different. So the trigger needs to depend on the memory of where you are now. It needs to know where it is now, and this is called hysteresis. And positive feedback helps us make such comparators which have hysteresis. So here I have a quick example. The way you change resistors is that you right click over them and you change the R to the value that you want. This changes the name of the element. So if I don't want to call it V2 but I want to call it Vn or Vi, that's a good place to do it. So let's label some outputs. And that's F4. And the simulation we are going to do this time is a DC sweep. So why a DC sweep? I just want to change the input voltage, let's say from, okay, actually minus 10 volts to plus 10 volts. So I get a really strange waveform, input as output. Well, that's not possible. Yes, so the reason is I have marked plus minus 10 volts but I haven't put a voltage. So let's do that. So notice, just because you call a node plus 10 and minus 10 doesn't automatically make it plus 10 volts and minus 10 volts. You have to add voltage sources that are plus and minus 10 volts. So now we run it. We check if that's plus 10 volts, it is, and we check that it's minus 10 volts, and we check both, and now we check the output and click it once more so everything else gets deleted. The output just stays at minus 10 volts and doesn't move. I'm moving the input, I'm moving it quite a bit, and only wait, there you see, only way at the end it actually switches entirely from 9.9 volt all the way to 10 volt. Okay, so so let's see what this means. So if my output is minus 10 volts, then there's a theory of superposition. You can set one voltage source to 0 and think of what happens because the other voltage source. So if I set this to minus 10 volts, the resistor divider will make this minus 5 volts. If I set this to plus 10 volts, it will divide it both plus 5 volts, so they'll add up to 0. So that's when there is a trigger point. But that hardly seems useful. Let's say I wanted to actually trigger when my input was 5 volts, and that's more reasonable, right? So if I wanted to do that, then I need to change the divider. So if I change this resistor value from 10k to 20k, and then I run the simulation, then it looks like I can trigger it at around 5 volts. Yeah, around 5 volts. So how do you determine this resistor ratio? So I'll just explain this once more. So I look at what is the negative voltage minus 10 volts, and I think of this as a resistor divider. So I do minus 10, I have a minus 10 volts, and I'm going to design it now. I have this resistor that I don't know, that it's 20k, and I have 10k, and this gives me 1 voltage, and this one is 10, everything in k, 10 divided by 10 plus r. The input, which is plus 5 volts, which is where I wanted to trigger, so it's plus 5 volts, and I have a resistor divider the other way. So this is 10k, right? 10k is closer to the 5k, this one. And then I'm seeing a resistor R, and so my voltage here, this is into 10, minus 10 into minus 10 volts, right? That one. This is all ohms, kiloohms, and this one is R divided by 10 plus R into 5, and I want the two to be equal. right? So I want the negative voltage to cancel out the positive voltage. I want to add at the same point. So superposition means I can take this voltage. It's like a voltage source now. It's not really dependent on the input. It's not varying much. So I can take this, find out what the voltage is because of this voltage, which is minus 10 volts, and I can take this 5 volts, and I can determine what is the voltage of the same node because of this resistor network, assuming this is at ground, assuming that is at ground. So here I assume that the plus 5 voltage was at ground, and here I assume the minus 10 voltage doesn't exist. Basically, it's at ground means it doesn't exist, and then I can just equate the two. So that gives me, this 10 into 10, this 100. I'm not taking care of the negative sign because they're adding and becoming 0, so I'm just looking at the magnitude. 100 divided by 10 plus r is equal to r into 5. I meant r into 5 divided by 10 plus r. So this 10 plus r cancels out with this 10 plus r, and this gives you r is equal to 20. And now I remember that this is all in kilo ohms, so that's 20 kilo ohms. That's a symbol for ohm. At this point it's fair to say, we assumed that the output was minus 10 volt. What if we had assumed the output was plus 10 volts? So when I'm going up, increasing, it triggers based off minus 10 because the voltage was minus 10, and so my trigger was 5 volts. But now that I have decided I want the trigger at 5 volt and this is 20k, I can figure out when I'm going down what happens. So when I'm going down, this voltage is at, so if I look at the plus 10 volts, that's plus 10 volts. So again, looking at the same nodes, plus 10 volts sees 20k first, so that's this value, and then it sees the 10k, and then I assume 5k didn't exist, so I've grounded it, and 5 volt or whatever the voltage is. So the other superposition part, I assume that part is 0, and so from here it's 5, whatever is the voltage we don't know. There's a 10k here and there's a 20k here. I've played around with the signs, but otherwise I've just worked this out. So that's 10 volts into 10 divided by 20 plus 10, which is this part, and then Vn into 20 divided by 30, which is this part. 30 30 get cancelled, 20 30, basically getting 5 volts. But what you're actually getting is Vn is minus 5 volts. Remember, the two have to cancel out. These are just equal. They cancel out when Vn becomes minus 5 volts. So how do I check that state? Well, here I was increasing, but if I decreased from 10 to minus 10, then if you look at the, I have to do that again, 10, okay, so I'm doing 10 to minus 10 which is going down, so this is actually decrementing. I put this away, I can bring it close. Okay, so right now this is the old simulation in which this is at 5 volts, and now if I run the simulation, then I see that at minus 5 volts is when it switches back. So it switches on at 5 volts and switches off at minus 5 volts, which is a fairly large range. You may not really need that large a range, but that's what this does.